那让我们欢迎 Alan。
Hi, everybody. I had hoped to prepare this presentation in Chinese, but I didn't have time, so I'm sorry. We're going to have to do it in English. Is that okay? Is everyone all right with me speaking in English? Okay, cool. Okay, so thanks for joining this talk. So I gave a talk earlier today about just to do an intro to Nix, and I see some of the same folks here, so thank you for joining. So I guess I want to preface this talk by saying, first of all, that I am not a core member of the Nix community. I just started using Nix last year, and I found that it was extremely helpful. So I started using it at work, and it's been a real pleasure. So I'm going to talk today about how to use Nix to optimize your machine learning model images, and in particular, minimizing the container image footprint. So before we get into it, let me pull up the slides, and I'll just tell you a little bit about myself. Okay, so I am a software engineer at Broadcom. My background is in a combination of software engineering, AI/ML, data science, and also quantitative finance. So these are some of the things that I've done over the past, I guess, almost 25 years now. I went to UCLA for financial engineering and studied computer science at Columbia. So to reiterate from my earlier talks, and personal interests of mine include Linux, Emacs, Haskell, Nix, plain text accounting. So basically, I love text editing, functional programming, and the plain text accounting stuff is also, I think it's a highly relevant component of finance in general and can be used for quantitative finance, but that's another matter. So just a little bit of background on myself. Okay, so to motivate the discussion, the context here is about deploying machine learning model images, machine learning models as images to serve in as a Kubernetes workload, for example, or as plain images. These things will serve machine learning models that you can access through your cell phone or your computer. This is an established, common, and effective pattern. So this was probably new, I don't know, like 10 years ago. So at this point, it's very, very common. When you do this, if you do this with compiled languages like Go or C, you can build statically linked binaries and just build an image with the binary. You don't need an operating system in the container image. And that's great. It's super lightweight. In machine learning, Python has become the de facto standard. It's the lingua franca for machine learning. And because it's an interpreted language, you cannot build static binaries, statically linked binaries. It's possible. I've spent some time looking into this, but it's really not easy, and there are a lot of trade-offs that you have to make if you want to go that route. If you were to build a machine learning image using Python with the interpreter installed, it's going to rely on a bunch of libraries, SSL, other cryptographic libraries, things that are typically dynamically linked, and they need to be present in the container. So it's a complication with Python. What you wind up with is really big container images. And then if you wanted to make those container images smaller, you could certainly do that manually by adding or removing individual components of that container image. But because most container images use some version of Linux that relies on the file system hierarchy standard, there's no library isolation in FHS. You have libraries scattered throughout /lib, /lib64 in various directories, and it becomes extremely difficult and tedious. So the problem that I'm looking at that I would like to propose a solution to is how does one minimize container image footprint across multiple images? So this came up earlier this year. I work on an LLM LLM-based chat feature inside of our SaaS product at Broadcom. And at the outset, so we have a model microservice architecture, and at the outset, those model microservices had a footprint of somewhere around 16 gigabytes across three ML model container images. And it's a lot. And one might argue that, well, in a SaaS context, it's not a big deal. Storage is cheap, but our organization wanted to support an on-premises air-gapped solution. And so that meant having to ship every one of those model images. And ultimately, with the entire product, the footprint of our product became something like 80 gigabytes, and then we have 16 gigabytes here just to support an LLM-based chat feature. So we got a directive to shrink the footprint. And because our models are written in Python, it's really difficult to do that. So how? So I looked into using Nix, and I found what seemed to be a pretty good solution. So how do you minimize the footprint of a multi-container image system? Okay, so I propose a solution where you can use Nix to do it. Nix store elements are immutable and addressed by content, and so that makes them nice atomic elements for you to manipulate container image contents. So you start by defining your container images with Nix. You then take your Nix store elements as the unit of observation, and then you proceed to optimally layer the images by those Nix store elements. So to elaborate on how this works, I'm going to do a quick review of what a Nix store path looks like. But I guess before that, quick show of hands, how many people have any experience with Nix whatsoever? Okay, a few. All right, that's good. So Nix is a pretty big topic, but suffice it to say that when you install software using Nix, all of that software will wind up in the Nix store. And the Nix store is a directory on your file system. By default, it's located at /nix/store. So this is already outside of the FHS standard. So inside of /nix/store, you will have a number of directories and files. And all of these directories and files will either be a derivation, which is a set of instructions for building a Nix package, or it's going to be a derivation output, a build output. It's the software itself. And in this case, I have a path to a CLI binary inside of a build output. So that build output has this two-part name here. The first part is the hash part, which is this really long string. It's a cryptographic hash. And that's followed by the package name, in this case curl, followed by the version number, 811-bin. So that directory there represents a Nix store element, and then the rest of the path is a path to a binary inside of the Nix store element. So inside of that curl 811 directory, this is a path to bin/curl. So if you were to have built curl on your machine using Nix, you might have this exact directory in there, and you can just invoke curl by entering this path. So this is a Nix store element. Okay, so in the course of minimizing your container image footprints, you can take each of these Nix store elements and you can identify which ones are common across images and then layer your images accordingly. So at the bottom, I've got a few Venn diagrams. There's a 2-set Venn diagram, 3-set Venn diagram, 4-set Venn diagram. So the idea is that each of these sets corresponds to the collection of Nix store paths inside of a particular image. And the more overlap there is, the more opportunity there is to shrink your overall image footprint. So I'm going to provide an example of how this looks. So over here on the right, I've got an example Venn diagram of 3 container images. And we're just going to call them R, E, and P. And here, following standard set notation, we've got in the middle, we've got the intersection of E, P, and R. So that's the set of all Nix store elements across these 3 images. And then outside of that, you have for example, E intersection R, set difference P, that's what the backslash means. So this is all of the next door paths inside of images E and R, but without the paths inside of image P. And you've got the same idea happening with the other paths here. And then the stuff out here is all of the next door paths that are unique to that particular image. In the table on the left, I have an accounting of the size of each of these images next to the size of each of these subsets. So that is to say that image E has a total of 3,343 megabytes, image P is 795 megabytes, image R is 2,299 megabytes. That's the bottom row there. And then every row in the body of the table will show you the size in megabytes of the particular subset corresponding to this diagram. So the trick here is to fully identify all of the elements of this partition of these three images, and each element is going to correspond to a next door path, a next door element. And once we break that down, then we have a theoretical minimum footprint goal that you can try to reach to truly minimize container footprint. So how does this look in terms of the overall image sizes themselves? So this table adds these three additional columns: unlayered, which is the size in megabytes of the images without layering. Duplicate shows you the size in megabytes of the duplicates of the raw next door paths. And then you have the final optimal size in the right-hand column. So when we started out this project, we did not use Nix. We used a version of Debian. And because we started out building those container images using Debian, there was a lot of stuff in there that we didn't need. I mean, I think there was like SendMail, like email servers in there, stuff that got installed by default. And our total image footprint was on the order of 16 gigabytes. So as soon as we started using Nix, because Nix doesn't install any unnecessary stuff, it only installs the direct dependencies of the software that you define, the total image size immediately jumped down to 6.4 gigabytes, 6,437 megabytes. And then, because that's still a lot for a single machine learning feature, I went ahead and I created this partition. I found that we have 2.3 gigs of duplication, and so I was able to reduce the total size, the total footprint, to just over 4 gigs. So in reality, I wasn't able to get it to exactly 4,065, but I got it to be pretty close. Okay, so let's proceed. So in theory, how does this look? So you can extend this idea to arbitrarily many images. You don't need to do just 3 images. You can do 4, 5, or 6 images. And the way that you would generalize this table into a situation, a system with more images, is you would enumerate all of the subsets within the partition of the number of images that you have. So in set theoretic notation, you're going to have these 2 to the n minus 1 subsets of next door elements. So, with n images, you're going. So in this situation, we have 3 images, and we therefore have the 2 to the 3 minus 1 subsets, right? 2 to the 3 is 8, minus 1 is 7. So we've got 1, 2, 3, 4, 5, 6, 7 subsets. And then in theory, you would just get 2 to the n minus 1 of however many images you have. You would have that many subsets. And so in this notation, if I denotes the number of I guess the particular subset that you're looking at between 1 and n. So if I equals the set 1, 2, 3, that's the intersection of EPR. If I equals 1, 2, it's the intersection of EP and complement R. So this is how you would do it. I guess in theory, if you wanted to create this programmatically, you would code up logic that computes this. So this is the idea from the theoretical perspective. So in doing this in practice, you certainly run across some real-world limitations. So for one thing, because you have 2 to the n minus 1 subsets within your layering, you have that many layers, you have 2 to the n minus 1 subsets, and therefore 2 to the n minus 1 layers, that number grows very quickly. So with 4 images, you will have 15 layers, and with 5 images, 31, with 6 images, 63 layers. So the number of layers grows very quickly. And if you're using Docker, you are going to run into a 127-layer limit, or at least that's the case in 2025. So that's really 7 images. So you may be able to use other solutions. I don't know if Podman has this layering limitation as well. If it doesn't, you can go higher. But you can imagine how if you're building this many layers, the computation time is also going to be pretty meaningful. So this is a consideration that you run into when you actually try this. So another thing to keep in mind is that when you are trying to when you're trying to optimize the image layering by NIC store elements, you really need to do that through NICS packages. You can't manipulate NICS store elements directly. So when you use packages, you may find, and I have found this, there's not a one-to-one correspondence between the package itself and store elements. So this is another area of difficulty that you're likely to run into. So this is all I have for material. I have a brief demo for you. So why don't I go through some of the demo material that I have, and then we can take a few minutes for questions. Okay, so let me jump over to another screen. Hold on a second. Okay, so I might need to put the microphone down for this. One moment. Yeah, good call. Okay, how's this for legibility? Good? Okay, cool. So I guess I'll just show you, first of all, this is a repository that we use on my team for managing NICS packages. So at this point, we're building our container images using NICS, and we're also building our individual Python software packages using NICS. We, of course, use open source software that you can find on PyPy, but not all of the PyPy software is in the official NICS repositories, so we have some derivations for that as well. So this is just a listing of our NICS, proprietary NICS packages project. So this is the directory that contains our container image derivations. So all of that stuff that I told you before, it's theoretical, right? I haven't written any software that will do this for you automatically. And clearly you can see that you can write software to do this automatically. It takes a little bit of work. So in the meantime, I have done this manually. And so the 3 images that we use to back our LLM chat feature is these 3 down here. So they're called TIA embedding service, TIA page nav, TIA routing. And those derivations define those images. But in order to define the layers that comprise these images, I have 2 additional NICS derivations here. You see that in the bases directory. You have TIA service base and TIA torch base. So TIA service base is something that contains REST API server code. And then TIA torch base contains some machine learning dependencies, principally PyTorch. So these get layered together manually. Okay, so this is one of those NIX files. And in particular, this is one of the base images, TIA service base. And so we didn't talk very much about how NIX code looks in this session. We talked a little bit about it in the 11:30 talk that I did earlier today. But NIX, because it's purely functional, all the code that you write essentially is a single expression. And so this is an expression that defines a function. So this is a function that takes 3 inputs, build end, Docker tools, Python 3, and then it'll build what's contained in the function body. So this is not a pure function, so to speak, for folks who are familiar with functional programming languages. Over there on line 9, you have a little read out onto the file system. So this reads the contents of a directory called model service data. But one way or another, this function will combine all of these elements and produce a Docker image that will function as an intermediate layer. And so the consequence of all this is that Docker image is going to contain a set of NIX store paths that will get used ultimately in the final image. Let me show you one more. So this is another derivation for a final image, and you can see here where let's see if I can get to it. So on line 29, TIA model service, which is the derivation we just saw before, figures in as an input. So this is how you do manual layering when you build Docker images. I'm going to move on to another example since we're running short on time now. Okay, let me type this one out. Okay, so I'm invoking a piece of software called Dive, which allows you to examine the contents of container images. It takes a while to load because these are all pretty big. This one's only 800 megabytes, but it still takes time nonetheless. Okay, so you have layers over there on the left, and then you have the file system contents for that layer over on the right. Okay, so this is the NIX store, and at the base layer, this contains just one element. And then over here, this is worth showing, so let me try to figure this one out. Okay, so incrementally, you will see that more and more of the NIX store populates as you proceed with adding additional layers. So this one is, this is probably, this may be an older image that I created in the past, which has many, many layers. But the images that we create today really just have 2 or 3 layers. So because we followed that theoretical approach that I showed a moment ago. Okay, let me show you one more example, and then let's take time for questions. Okay, so this is just some data science style analysis of the layering that we accomplished in one of our iterations. So up here, it's got some data on what is in the contents of these three images. So the images are written as, the file names are result-layer data, result-2, result-3. And so you can see that these images have 136, 68, 137 NIC store paths across this many layers. And then here's that the subset partitioning that I described a minute ago for these three layers. So this is just an accounting of a realized set of images. And then you can see the individual NIC store paths over here in these listings. So the unit of observation that we're using in order to minimize container image size is these NIC store paths. So the analysis code here has gone through and enumerated each of those elements and added up the different storage footprints for these subsets. So if I scroll down a bit, so we have the optimal layering here for comparison. So in this particular realization of what we did, the optimal layering came out to be 3,881 megabytes, though we were never really able to accomplish this because you cannot directly manipulate the NIC store paths. You can really only manipulate NICs packages. Okay, so that's all I had to show for you guys. I think we have a few minutes for questions if anyone has any. Do we have a microphone, or should I? Oh, okay. Okay, yeah, that works too.
So when you modify one of the layers, say base layers, how does that affect the build time? Or how is the build time accurate?
So when you modify the base layers, how does it affect the build time? I mean, in my experience, the build time does not differ very much from, I don't know, a standard build time using like Docker tooling. But there are a couple of differences. So for one, with NICs, you'll notice when you use Docker, layers get cached. And so if you've built a layer once, it doesn't need to build it again because it's already present. And NICs does the same thing, and I think in a way more robustly, because in addition to caching the layer data, it will also cache, so to speak. It'll also keep a record of the individual pieces of software that went into the layer. So in that sense, it's better. One other thing I've noticed that I think is a downside of NICs, potentially you can call it a downside, is that if you use NICs a lot, you will find that it has a tendency to recompile software, especially if the software that you're building is not already present on a binary cache server. It's not already something that somebody else is using. So for example, when we started using GPUs at work, whenever I tried to run this on my NICs machine, I had to rebuild Python, or I think I had to rebuild both Python and PyTorch in order to integrate the NVIDIA drivers. And that took forever, but it turns out that there are also open source projects that provide caches of PyTorch with NVIDIA support. So in general, build times are long. They can be long depending on what you're building. Repeat builds tend to be very fast.
So is the dev environment also set up with NICs, or we need to translate to the standard Python log file into the NICs configuration afterward?
So our dev environments are written in NICs. So let me try to pull this up again. So this is our NICs repository. So it's no surprise it's going to be written in NICs. But every one of our repositories has this flake.nics and flake.lock file, which defines the development environment. Not everybody on my team uses NICs. We use NICs in the CI/CD pipeline, so that environment is also coded in NICs. But because some of my teammates like to rely on UV, I mean, I also use UV. We use those side by side. So essentially the way this works is that for the Nix part, you have your flake.nix and your flake.lock. For any Python project, you have your pyproject.toml, which defines dependency constraints. And then if you're using UV, you can also separately generate a uv.lock file, which will define a set of specific version numbers that satisfy the pyproject.toml constraints. So our workflow in these projects, in order to support both Nix and UV, our workflow is to write a Nix, like flake.nix file, include UV in the flake.nix file so that, Nix is installing UV, you've got the same version across machines, and then we run UV to generate the lock file. That's a pre-commit hook so that every commit has an up-to-date lock file, and we check those in. And that way, when one of my teammates who only uses UV wants to work on the software, they have an environment that's ready to go. If they modify the dependencies, then the pre-commit hook will update uv.lock, and the CI pipeline will ensure that Nix is still working. Question here. I think we probably have time for just one more.
So I'm trying to understand. So this example uses PQR 3 layers.
Yes.
And then, so in practice, is it optimal or is it better to have more layers or fewer layers? Is 3 a magic number here?
So there are probably some important systems engineering considerations when it comes to layering. And those things I've not spent a whole lot of time thinking about. So this, I guess deployment, caching, image transmission. When it comes to the goal of just minimizing storage footprint, there's no reason to have, any more or any fewer layers than that. In theory, exactly 2 to the n minus 1 layers will suffice. Okay, I guess we're at time, so we'd better wrap it up. So thank you very much for joining the